Hi everyone, and welcome to this seminar. So today we have the pleasure to welcome Samik Mitra from IIT Guwahati. And Samik will talk about an overview of the magnetized advective accretion flows around black holes. So if you have questions during the seminar, it's fine to ask. If you prefer also to raise the hand, then I will inform Samik. And then if not, there will be questions at the end too. So please go ahead, you have the floor. Thanks a lot for being here.
Yeah, thanks, Jordan. And I'll also thank Hector and Professor Carlos Herderiro because they allowed me to give the opportunity to present here. So today I'll be discussing about the overview of magnetized advective accretion flow around black holes. And here are my collaborators with whom I'm still collaborating. And there are some other people also which I collaborate. I forgot to mention their name here. And I am a PhD student. I was a PhD student at IIT Guwahati. And this is just a brief about my profile that I did my bachelor's from University of Calcutta. Then I moved to University of Delhi where I did my master's. And there I actually was introduced to the theoretical physics and the depth of plasma physics and astrophysics and mainly the accretion theories. So, and I also have some preliminary experience with the astrophotography as well. So this motivated me to work more on towards the accretion and all these imaging techniques. And then I joined IIT Guwahati with Professor Santobrata Das, where I mainly worked on dissipative accretion flow around black holes and magnetohydrodynamic and hydrodynamic flows incorporating general relativity. And during my PhD, I was also fortunately awarded with this Prime Minister's fellowship. So that's the whole idea of about my background. And this is the thesis title of my thesis, that magnetohydrodynamic and hydrodynamic studies of relativistic accretion flow, which I recently defended on 6th February. So that's a positive thing that happened recently. And these are some of the works which I did. So as you can see in my thesis title as well, it is discovered with the hydro and the magnetohydrodynamic part. So these are the works with the hydro concept where I'll be mostly worked with this conduction, the effect of thermal conduction of accretion, then the dissipative shock in accretion flow. And also there is this interesting work which, I really enjoyed, that is the accretion dynamics in the post-Newtonian gravity. So this is, I won't be discussing the hydrodynamics part today, but mostly I'll be focusing on the MHD part, where I have developed the transonic or transmagnetosonic accretion solutions around Schwarzschild as well as maximally rotating Kerr black hole with and without shocks, which I'll be discussing. And also I have some interest in the particle dynamics and QPO analysis, which I also give a brief about it at the why this particle dynamics approach is also pretty interesting to explain the quasi-periodic oscillations in the around the black hole sources. So yeah, so this is a interesting image. I think we all know about the right side image, which is produced by the Event Horizon Telescope. It is about the M87, and this is basically to identify the event horizon of a black hole. And this is for M87, as you can see. But this is a direct image that has been observed by these ground-based radio telescopes of EHT. But we always felt that these are very extremely costly and as well as extremely tedious job to and complex as well to maintain and image all these things. But the easiest way is always to find the surrounding matter which are trapped by the immense gravitational potential of the central compact object. So the idea is not to go direct observation, because we can do direct observation with the help of EHT, but the indirect detections are much more easier for us. And this is just a funny image to show that the polished donut or the torus-like structures are pretty much similar to this image. That's why I just put it here. Now, about the trapped matter which I was discussing. So let's say there is this immense gravitational potential about the central object, and there is this binary companion star. And from there, because the strong gravitational potential is there, this matter is trapped and it tries to fall into the central object. But because of the angular momentum's presence, it cannot fall radially. Instead, it falls via spiraling nature and eventually forms a accretion disk-like structure. Now, the question is, in order to observe black hole, why accretion study is very important? That is because here the gravitational energy of this infalling matter is being converted into radiation, and accretion is the most efficient process to do that. And you can see by simply by this equation where delta is the energy that is converted from gravitational to the radiation, and this eta is the radiation efficiency or radiative efficiency. This is the accretion rate, that is the amount of matter with time, how much matter is actually falling into the black hole with time, that is the thing, and this is the velocity of light. So if we consider this is basically the rest mass kind of energy, rest mass energy kind of stuff with time, then eta will give us the amount of conversion efficiency. And we know that for a extremely rotating curve black hole it could go up to 42%, where for a source shell black hole it could go around 5.7%, which is even higher than the nuclear fusion process that we know. For nuclear fusion it is only 0.07%. So we can understand that why accretion is most important in this sense. Now, there are also, if we talk about the different, different kind of objects like supermassive black holes, stellar mass black hole, white dwarf, protostar, planets like Saturn, Moon, we all see always that different kind of accretion disk formation. So the disk is basically universality in the whole universe. So we can see that. So therefore, it is pretty interesting to study the accretion disk because it's a general phenomenon. Now, in order to observe black hole, there is this recent Nobel Prize winning problem where Andrea Ghez and Reinhard Genzel, they actually worked with this Keck and UCLA group. They just studied these nearby S2 stars or all other stars, and they studied using simple Kepler's law, try to find the central object's mass, and it came out to be of the order of millions. So this suggests that the such highly compactness can only be possible if the central object be a black hole. But we are still not interested in this talk or in my thesis, not about the particle approach of to determine the central object's behavior or something. So we are mostly sticking into the accreting part. Now again come back to the EHT images, because this is very interesting observation by them, as this shows the first ever visual evidence or the imprints of magnetic fields around the supermassive black holes. So these lines are basically, as many of you are well known about it, these are basically the Stokes field line around this M87 and also the Sagittarius A star image. And this clearly suggests that there is this strong synchrotron emission is happening, and that suggests that magnetic fields are present. So since this hot, like these photons and all these things that is coming around this event horizon, that has to come from some plasma sources, that eventually suggests that since this plasma has the magnetic field imprints in it, so accretion and magnetic field are coupled to each other, and when we study accretion we need to study the magnetohydrodynamic part with it. So that was the initial motivation for me. Now the idea is what the magnetic field plays the important role in accretion disk, because initially the idea is that matter starts from the Bondi radius to fall into the central object, and in order to do that the angular momentum has to transport outwards. So initially Sakura Tsunai proposed the anomalous viscosity prescription, where alpha was the black box, no one knows about it. But Balbus and Hawley actually proposed that in a differentially rotating disk, if we consider, let's say, two blobs of plasma, where the inner part is having higher angular velocity compared to the red one, and if they are connected with a magnetic field line, because the flow is actually in ideal GRMHD, ideal MHD condition where the field lines are frozen in the plasma, if you consider that approximation, then if you release this blob in this disk, then you notice that the inner blob will move faster compared to the outer one, and in doing so that magnetic field lines are get stretched. And what is basically happening, these magnetic field lines, since the blobs are keeps on moving and there is a torque getting developed within these two surrounding layers, they are actually transporting the angular momentum, because the inner blob will lose its angular momentum and transport it to the outer one, and it keeps on transporting the angular momentum to the outer part. Now as the angular momentum is getting lost by the green blob, it keeps on falling into the subsequent layers and the inner part, and whether this outer part is gaining the angular momentum and keeps on transporting the angular momentum to the subsequent layers and keeps on falling into the central object. So effectively the accretion picture is something like this, that angular momentum is going out and the mass is keeping on falling. Now in order to visualize all these things, the general relativistic MHD simulation is also very important tool to visually showing the time evolution of the disk and the dynamics of the accretion flow. And also there is this beautiful illustration where it shows that the magnetic field is also help, I mean, could also help in launching the extreme, I mean, highly streamlined jets from the accretion disks, where you can see this magnetic field lines, how it helps in launching the jets, and also the power of the jet is directly related to the magnetic field, also with the black hole spin. So this overall suggests that the magnetic field and I mean is important, and the GRMHD could show us lot of interesting features. But there is an interesting question that what is the possible topology of magnetic field in an accretion disk? Because if we initially if we thought it's a simple problem because there is a accretion disk in the equatorial plane, if you release a blob of mass or maybe a particle, the matter always has a possibility to have a dominant motion along the toroidal direction or the azimuthal motion compared to the radial one. So that's how Oda et al. They started their work long back in a series of paper with the simple toroidal structured magnetic field. But eventually, when they wanted to explain the jets or maybe the Blandford Payne winds kind of stuff, they need different kind of poloidal configuration like this or maybe some sort of inclined nature in around a thin disk. But also there is more popular like structure where the GRMHD simulation deals with these torus like problems, where they started with uh, dipolar, quadrupolar, and even multi-loop, alternating loop kind of structures. They also get some successful results, but all these papers were directed towards different problem to address different aim of their target, is like in order to explain different physics out of it. So the idea that we developed from it, that we need to find a analytic solution which simply suggests, instead of starting with a simple structured magnetic field, from the equation point of view, we want to understand what sort of magnetic field is really developing within the accretion disk with our analytical model. Now, again, the question will come, why, since simulation is already working, why we need to go with the analytic model? So there is a beautiful illustration by Professor Charles Gammy's slide, which I heard from the one of his talk, that it suggests if you consider the galactic center and the EHT resolution could solve up to this resolution, let's say, and the GRMHD model could go up to here, and we are somewhere here around 10 to the power 10 gm by c square. Now we know that when the Roche-Loeb overflow or some sort of accretion is happening, typically it starts from the Bondi radius. So if you see, it's more or less almost 10 to the power 6 gm by c square, like 6 orders of magnitude you have to travel or you have to simulate that amount of length. And also you have to do a time evolution that is also typically of the order of similar, like 6 orders of magnitude. So this is computationally very challenging in order to do that. However, if we look into the semi-analytic accretion solution, it is very easy for us to start from such high radius and the matter eventually fall into the central object. So large scale Frieding process, in order to understand the background of it, we believe the semi-analytic model could provide us some serious insights. So with this motivation, we start with our first work, where we simply consider a disk which somehow looks something like this. This is axisymmetric, and we consider a steady state. That means no time evolution is there. And since we consider the disk is always maintaining a vertical equilibrium, that means disk is maintaining, if we consider the half thickness of the disk is h, and this is the radial extent of the disk, the h over r always is less than, very less than 1. So this is suggesting that the disk is more or less maintaining close to the equatorial plane, and for that approximation we consider that theta is almost pi by 2 and del theta is also negligible because there is no motion along the vertical direction so far. Now we, as we mentioned, that the flow is in ideal MHD, and mathematically we know that this is the illustration for this mathematics for it. U mu is the forward velocity and B mu is the fluid magnetic field in the fluid frame. And these are all these normalization constant. UR is less than 0, which shows the inflow, and U theta is 0 because no motion along the theta direction. And since we are now left with 3 magnetic field component, BR, B phi, and B theta. But for the time being, since we are doing it for the first time, we thought since the flow is already in the equatorial plane, it is better to start initially with B theta to be 0. And let's see in the presence of BR and B phi how the accretion dynamics develops within the disk. So that was the background assumptions that we have taken. Now, these are the standard equation that we start with. This is the continuity equation, the energy momentum tensor equation. And here you can see this energy momentum tensor is built with these two components, the GR and the MHD part, combining the GR MHD energy momentum tensor. And we have this homogeneous Faraday's law, which is effectively the Bianchi identity. And here you can see there is this like two equations could be there. And with the previous assumptions that we have taken, that del theta is 0, del t is 0, and del phi is 0, we only left with mu equal to r option. And with that, if we do, we will see that we have 6 variables to solve, but we have 5 equations, one from here, two from here, and two from here. But we have 6 variables where there is radial velocity, phi velocity, gas pressure, density, Br and B phi. So we have 5 equations but 6 variables. Therefore, we need a closure equation which will be provided by the equation of state, where we consider a relativistic equation of state, as you can see here. What do I mean by the relativistic equation of state? That is basically something like this. This gamma is the adiabatic index. And if we consider here somewhere is at the origin of this coordinate system, the black hole is there. The adiabatic index is not constant, it is radially varying. So close to the black hole, it is reaching a trans-relativistic limit around 1.44 by or 13 by 9 kind of stuff, and outside it is going close to 1.5. So it is showing a trans-relativistic nature. So this actually make our computation bit complicated, but we somehow solve it with a simple technique of this conversion with this velocity gradient, temperature gradient, angular momentum gradient, and the magnetic field gradient. So these are the most important equation that we have, and these are the conserved equation that we get from the conserved equations. There is the energy flux, angular momentum flux, and the mass flux or the mass accretion rate. And we supply these initially these quantities, and we eventually solve this coupled 5 nonlinear differential equation to get the equations. So this was reported in the first paper of our work. So here in this coordinate system, we plotted the Mach number, that is the fast magnetosonic Mach number here. And this is the radial coordinate, and in the origin the black hole is sitting, and we considered a Schwarzschild black hole for the time being. And what we did, we fix the energy, angular momentum, and fix some m dot value like the mass accretion rate. And we also fix some B phi, that the toroidal magnetic field, at some of the outer edge, which we consider at 10 to the power 3 gm by c square. And we keep on playing with the radial magnetic field at this radius. And we see whether the subsonic flow fall into the central black hole with a supersonic Mach number or not. And we see particularly at a certain value, which is 3.55 Gauss, we notice that the flow initially starts with a subsonic nature and eventually getting supersonic by passing through this inner sonic point. And this was for the first time we reported such transmagnetosonic accretion solution in GRMSG framework. And we keep on evolving our flow with different magnetic fields, and we notice that the solution topology keeps on changing. But beyond a certain limit, we notice that the flow no longer passes through this inner kind of critical point. Instead, it goes far away, which is somewhere here, which we call as the outer critical point. So we get the global topology of GRMSD accretion solutions for the first time. And we were interested to understand for these inner critical point accretion solutions, what will be the magnetofluid variables look like. So we start for a 10 solar mass black hole for this case, and we notice that close to the black hole it reaches almost 10 to the power 6 Gauss. So as you can see here, but we already know that development of magnetic field within the disk is mostly important, mostly expressed in terms of plasma beta, which is the ratio of gas to magnetic pressure, and which is showing very interesting behavior to us. So if you are far away from the black hole, both your gas pressure and magnetic pressure are negligible to each other. And I believe that if we go even further outside, they will probably maintain a equipartition of energy between them. That's how you can see that around 10 to the power 3 gravitational radii, beta is almost close to 10. But it eventually, as the matter begins to accrete, the gas pressure starts to develop rapidly and beta increases. But there is a catch in panel C. If you notice, particularly around this region, around 100 to 200 gravitational radii, you see that the toroidal magnetic pressure suddenly starts to dominate. And as it starts to dominate around this region, you see that the beta starts to drop. So this eventually suggests, or we claim from our plot as well, that maybe in the equatorial plane, the toroidal magnetic field is the most dominant one, and as it starts to dominate, it governs the accretion dynamics, and this is maintaining the flow to become magnetically more strong or more dominant. That's how beta is keeps on dropping, and it eventually go close to 1. So this is pretty interesting for us, and also we try to plot the Alfvén speed here, which also shows a similar measure to the magnetization of the quantity. If we consider enthalpy is close to 1, so this is the typical behavior of the magnetization as well, which shows that flow starts around maybe 10 to the power minus 2, but it goes around almost 10 times or more than 10 times close to the black hole. So this is showing that the toroidal magnetic field is effective in developing the magnetized nature within the disk. And since there is a continuous interplay between the radial and toroidal magnetic field within the disk, we understand that there has to be some sort of angular momentum transport within the disk. But we remember that we do not have any alpha present in our disk, we only have the magnetic field. So we try to understand in a subkeplerian flow whether this Br and B5 was sufficient to transport some sort of angular momentum, and it shows yes that the angular momentum is not constant, it eventually has some sort of transport. And since we see some sort of transport in angular momentum, we try to estimate whether what kind of viscosity will be developed within the disk. Also, although it is a crude measurement, we only did simply taking the ratio of Maxwell stress over the gas pressure, which obviously for our 1D case, it doesn't make sense to take any volume average or any kind of averaging. So it is this definition what also Sakura Tsunoy followed, but they have this vertical integration as well. So we have a similar measure, and we notice that alpha is not constant, and it is mostly determined what kind of magnetic field is there within the disk, and it shows the radially varying behavior, which also some sort of simulations also reported for the magnetic viscosity case. So this was all the claim that we have in the first paper of our work. Then I'll move to the second part, where we stick to the same equations, but we try to understand that if you remember the equation, there is this flow with have both inner critical point as well as outer critical point. Now there is for a given energy and angular momentum, if the flow has both the options to pass through either from the outer or also from the inner point, which critical point the flow will choose, and what will determine or what will resolve this degeneracy for the flow. So then we realize that the entropy could play a very interesting role. First, I'll show some movie here. As you can see, this is the Mach number, but this is a purely hydrodynamic case. The flow starts from the outer critical point, gets supersonic here, and you see that the flow, this magenta curve has a tendency to go outside somewhere from here, but it didn't go through this magenta curve. Instead, it chooses another path where some sort of discontinuous jump is happening, and again the flow passes through this inner sonic point and giving a global structure something like this. There will be the green branch, then there will be this jump, and then this magenta curve, but it avoids to pass through this magenta curve. Why is it so? In order to understand that, we calculate the entropy of both these branches, and we noticed that this green part has higher entropy compared to this part. So that's how there is this kind of shock is happening, and which is telling the matter to follow the thermodynamical laws, like the higher entropy path they should follow, and that's how there is a physically motivated standing shock develops within the disk. And you can see that there is some sort of change in velocity, temperature, as well as in the aspect ratio within the disk. So this is showing that after the shock, there is this density compression is happening, there the temperature as well as the puffy nature is forming within the disk. But why is it happening? Because if you consider the accretion flow, there is three most dominant forces that will be there. One is this magnetized pressure, like magnetic pressure force, then the gravity force and the centrifugal force. But if we compare the gravity and centrifugal force, these are the more dominant one compared to the magnetic pressure case. So we realized that around a certain radius in the close vicinity of the black hole, these two forces tries to balance each other. As such, there is no force condition is there. So if there is some sort of no force is happening, what will happen? The matter will keep on coming, but there is no force, so the flow cannot continuously pass into the inner part. As such, it is facing some sort of virtual barrier, which is basically due to the centrifugal barrier that is developed within the some region of the disk, which is close to the black hole. And as the matter keeps on coming, what will happen? The matter keeps on coming, it is not getting a path to move in the radial direction. Instead, it revolves. As it revolves, the matter keeps on having a puffed up nature, where you can see at the effectively like puffy nature of the disk. And also beyond a certain region, I mean, when the density reaches the critical limit, the matter, the centrifugal barrier no longer is able to hold the matter for a long time. Eventually it, you can see there is a clear distinction from this kind of flow with this, like this outer cold flow to inner hot flow. And here you see a transition region from cold to hot part, and you see some sort of advective region also here, which is developing much more hotter, much more denser, and effectively we call it as a post shock corona. So that was our motivation, that this sort of behavior is developed within the disk. Now, why this is important? That is the major question. So from the observational point of view, if you consider the X-ray binaries, we see the hysteresis curve here, and we notice that the uh, any X-ray binary could go in this outbursting phase. It could travel through four different phases, like mostly from hard to soft state, and it keeps on revolving it. And they have this spectra which looks some sort of like this. And in order to explain this spectra, it has been observed by several papers that there is a hot flow which is bit puffed up from the cold standard disk is necessary. And there I believe that the shock model could fit. And particularly I'm not talking about any shock model, but magnetized shock model, I believe it could fit here, because it is, it can explain both the soft x-rays that is coming out from the cold part, and also the hard x-rays which are getting inverse comptonized from the soft photons that is coming from the cold part of the disk, getting inverse comptonized by these hot electrons, and eventually you will get it. So it is pretty much necessary for us to have such sort of corona's presence. So that was the initial motivation, and we also did some sort of work with the hydrodynamic flow from our analytic model using a Pluto code. Sorry, using this Pluto code, as you can see, we start with some sort of energy and angular momentum for this analytic solution, which is in blue curve, and we give the same set of initial condition at some injection radius, which is around 400 gravitational radii, and we noticed how the flow will evolve. And you see here some sort of flow coming back and going, like forward and backward thing is happening, and there the velocity jump is there, and also if we calculate the pressure density, they also show some significant jump. But most interesting point, when we plot the Mach number profile corresponding to it, we notice that the Mach number fits with the analytic result very well. So this suggests that the for hydrodynamic case it's pretty much well understood. But for MHD case, we still have to explore this shock dynamics with the simulation part. That still remains somewhat open, which I wanted to explore in future. Now, for the analytic part, I already resolved this for the shock case, where these are the governing shock condition, where the first four is the Rankine-Hugenoid shock condition, and for magnetized case, you need this additional two magnetic flux conservation and isorotation conservation to be maintained across the shock front, and you get some sort of this kind of behavior. As you increase the magnetic flux, these phi quantities are basically the magnetic flux, which you can simply understand from here. So if you basically increase the phi, that means you are increasing the net magnetic field which is flowing inside the disk. And as the magnetic field is increased, magnetic pressure will be increased. And in order to maintain the pressure balance across the shock condition, what will happen? Since the overall pressure is increasing within the disk, the shock front is getting pushed outwards. So this has been compared for both non-rotating as well as for maximally rotating black hole. And we also plotted the entropy value for it. And we noticed for the shock case, always the entropy remains higher compared to the shock free case. So that also justifies our statement. Now there is this interesting behavior that we can also understand from here. As you can see, we try to explain our flow in terms of the power law indices. So before the shock, the flow is called as a pre-shock, and after the shock, the flow is called as post-shock. So you see, if we compare like the density, temperature, then gas pressure or magnetic pressure, and then eventually the magnetic field for the toroidal case, we realize that the pre-shock profile always follow the self-similar power law, which Narayan one their review they have provided long back, and it's typically the same irrespective of what sort of spinning black hole or non-spinning black hole you have. It always shows the outer part, the pre-shock part doesn't care about the central black hole. But after the shock, where the flow is already in the inner part and it got the effect of the central object, you see some sort of steeper nature of the power law profiles. So, which are pretty interesting. And I was thinking, since the inner part after the shock flow is pretty hot and dense, we could actually try to implement these power law profiles in the ray tracing code in future to understand what could be the possible differences, or whether there will be any sort of different imaging EHT images could be produced with this kind of radial profiles will be there or not. So I am also very interested in to look into those kind of feature. Now, okay. So this is also an interesting profile for X-ray binaries. So there are some models which suggest that the spectral state transitions could be controlled by the location of this transition radius or the shock location from the cold flow to hot flow. Then the compression ratio, which is basically how much density is getting compressed between pre to post shock flow, and also the jump in the temperature. These three quantities could be very important to explain the spectral states. Some of the papers already playing with this sort of parameter, and they call these as shock properties. So we realize whether magnetic field could affect the shock properties or not, and we see that if we change the magnetic flux, the shock properties also keep on changing. And that actually makes us to say that since magnetic field controls the shock properties and shock property control the spectral states, so we can say the magnetic field eventually could control the spectral properties of the X-ray binary sources. So this needs to be explored in detail using simulations as well. Now, since we are dealing with the magnetic flux, we tried to give a passing comment in our paper whether, although we know that we do not have a poloidal magnetic field within our disk, but can a shock accretion flow possibly reach the mat state? So we find Sadowski's paper, and there we find that there is an estimation for a given mass of the black hole and the accretion rate. What is the maximum limit to get a MAD value? So we do it with our analytic model and we calculate. It is already 10 to the power 18. We can see it is almost 3 orders of magnitude difference. And for a 10 solar, we consider a 10 solar mass black hole with a accretion rate of 10 to the power minus 3 Eddington. And for that, when we calculate the maximum flux that could be accumulated in the black hole for our case, we noticed that it is almost 2 orders of magnitude lesser what Sadowski has predicted for the MAD case. So this is obvious, right? Because we do not have the b theta quantity in our case. So we just say that b theta is necessary to achieve the MAD state, and where we wanted to explore the analytical jet model from our 1D solution in the 2D problem. Like we have all the radial profiles present in our case. And if we now consider that disk is already there, but if we want to understand the vertical profile, like about the jet or something, then it could be interesting to deal with again another 1D problem using a b theta. So something that I am right now currently working on. This is the background of MAD and SEN, which is clearly showing that what are the distinctions between these two. And this clearly shows that for a MAD case, you will have a strongly collimated jet, and also the magnetic flux is much more higher, almost 10 times higher to be precise. So these were some background and some interesting paper, which if someone is interested, they can look into it. Okay. Now, as I was mentioning earlier, that I did some sort of particle dynamics analysis as well. So the idea is, if you remember about the shock flow, there is this transition radius, right? And in hydrodynamics case, if you remember that this transition radius keeps on oscillating, although beyond after certain time, it eventually boiled down to the same radius what analytic solution predicted, but it's never, it's always not the case. Sometimes it keeps on oscillating. And this sort of behavior is also observed in the case of truncated accretion disk, where the flow is coming, magnetic flux is developing, that flow again gets stopped by the strong magnetic field. Again, the magnetic field emerges out because of the mad state is reached. Again, flow could go continuously close to the black hole. So there is a continuous oscillation is happening. So if such sort of oscillation is there, many people try to explain the quasi-periodic oscillation around X-ray binary sources. Now, with the help of this QPO basically somewhat looks like this. This is a power density spectrum profile, which we call also a PDS. So here, when we plot the Lorentzian of this flow counts in the Fourier space, we can realize that there is some sort of peaks are there. Now you see there are two different peaks, and these two peaks always known as a twin peak QPO, and this twin peak QPO maintain a ratio of 3:2 with each other, with the peak value. Now, my motivation with this particle dynamics was, if we consider a Keplerian disk, and in the Keplerian disk, if we consider some perturbation in the equatorial plane around the stationary orbit, we could also predict different orbital angular velocities, like Keplerian one, radial velocity, radial omega r, omega theta, and omega phi. And with that, we could always define what is the upper cutoff frequency and lower frequency. And from there, we use a MCMC analysis to predict or try to fit for a given source. So for this, we fit with the GRS source with the upper and lower QPO frequencies, and we estimate the mass of the central object. And if we consider the central black hole is a charged black hole, then what sort of charge will be there? And also the small q represents if the particle is a charged particle. So this is just a simple illustration that using MCMC analysis and the observable, we could also estimate what could be the central object parameter, and as well as the what sort of particle and what sort of charge could be there. And this R is basically where the oscillation is happening. So this is just to show about the application of particle dynamics. Now, there is this interesting work that also we did with a dissipative shock. So as you noticed that I have mentioned earlier, that if we have to explain a shock, you need to satisfy some conditions, where you notice that this energy flux has to be conserved across the shock front. But if you notice this observed image or the cartoon image here, that after the shock, that the flow already get puffed up, and as the flow gets puffed up, it is getting much more unbound in general, right? Already we are dealing with a low angular momentum flow, so the flow already is unbound in nature, and if the flow is already getting puffed up, it has a tendency that it could dissipate or like deplete some sort of magnetic flux, maybe some sort of energy. It could be possible because it's already unbound. So with that idea, we noticed if some sort of energy could be depleted away from the shock front, what will happen? And we realized that the shock dynamics keeps on changing depending on the energy it is extracted out from the shock front. And that energy for a non-rotating Schwarzschild black hole, it is almost could reach up to 1%. For a maximally rotating curved black hole, it could go up to 4.4%. And with this idea, we actually tried to fit with a wide range of spin value, wide range of mass accretion rate starting from 10⁻⁵ to 1 m Eddington. This cyan patch was calculated for a wide range of mass of the black hole, and this was basically what is the shock luminosity that we could get simply by calculating how much delta E we can extract. And we tried to fit with all the black hole X-ray binaries, AGNs, and some intermediate mass black holes also we tried to fit. And we see that some sort of datas are getting fit for the AGN sources. So since we were able to fit some sort of result of the observed data, although our calculation initially was a non-dissipative flow in a sense that it has no viscosity present within the disk or no cooling is also there. So obviously we try to keep on improving this, but there is an interesting situation we realized for the same set of initial condition about the hydrodynamic case, which is reported in the left plot. We repeat the same thing when we incorporate the GRMHT, the magnetic field part. We noticed that for a given similar setup, only by incorporating a magnetic field within the disk, there is an enhancement of the energy extraction. So this suggests to us, or I got an idea that if we could calculate that how much of magnetic flux and how much of energy could be extracted in presence of the magnetized disk. This could actually enhance these values from 4.4% to even higher. So I just wanted to explore it, that whether there is some sort of modification with it or not. Now, finally, there is this interesting research that is currently I am working on, because earlier I was only working with the GRMHD framework without involving any cooling. But right now, in a physically motivated disk, you should have some sort of radiative cooling processes to be present. And the simply, if we can always add in a optically thin limit, if we want to address the cooling processes, it is very easy to just add the cooling terms in the right hand part, where Q is the cooling processes like Bremsstrahlung synchrotron, all these cooling rates, and mu is a force velocity. This is a simple assumption that we could always take care of. And then we did initially with Bremsstrahlung and synchrotron, and we noticed about what is the effect of the temperature profile. So we see that the black one is when cooling is 0, and as we keep on adding the Bremsstrahlung, the temperature drops suddenly. And then if we have the synchrotron, it shows that the inner part is highly dominant because of this synchrotron, because the magnetic field is much more strong in the inner part of the disk. So this motivated us to calculate further the spectral energy distributions, and we noticed, this is just a simple report which will be appeared soon in the Marcel Grossman proceeding. So I just reported that the inner part of the disk contributes the most for the spectral energy distribution. As you can see, the red curve, which is from the horizon to 10 gravitational radii, that actually contributes the most to the ACDs compared to the other radius, and which is obvious. And this again suggests one interesting point, that the low angular momentum flow is pretty important here, because the flow not necessarily has to be Keplerian, because Keplerian flow always truncates at the ISCO radius. But the flow eventually has to fall because we are dealing with plasma, right? So the plasma should fall close to the event horizon, or maybe go into the event horizon, right? But this inner part, ISCO to the inner part, in order to explain that, the flow has to have a low angular momentum flow. That means at every radius, the flow doesn't have the Keplerian value. Instead, it has a much lower value than the Keplerian one. So if we do that, that also justifies our statement that low angular momentum flow is pretty important to explain the inner radiation coming from the inner part. And also we compared the shock and shock free case, where we realize that since for the shock the density and the temperature is getting much more higher, you see an elevated ACD profile, which is in the black and red curve. You can see the distinction between these two. And obviously, if we want to understand, this is the Bremsstrahlung part at the higher energy, or higher frequency, and this is in the lower frequency part is the synchrotron region. Now, during my visit to Shaho with Professor Fuguazi, what I was working on in the MHD case around a rotating black hole, to get a composite spectra. Like, we have synchrotron, we have Bremsstrahlung, but we were missing about this Compton part. So this we have worked with him about the development with the Compton part, with a simple fraction of the from the cyclosynchrotron, some fraction of part is getting converted into the Compton part. So that's how we are not using any simple, any complicated Monte Carlo technique there, but we are using some sort of fractional value that could be used to, generate some sort of Compton scattering process as well. So this was the radiation part. And finally, I will be discussing that recently I was working with Dr. Bhupendra Mitra in Athena++ code during my PhD time, where I started with some sort of vertical magnetic field structures around a FM torus. And there I was trying to understand if we change the plasma beta at the inner edge of the torus, like for these three different cases, where the black one has the strong magnetic case, and the blue one is the weakly magnetic case. If we deal with that what sort of effect will be there in the uh, accretion disk processes around very close to the non-rotating black hole. That is the initial catch. But initially the idea developed in this way, that if you have a thin disk, the thin nature of the disk has a problem, because if we evolve it with the simulation, it doesn't maintain its thin nature, and it gets the thermally unstable nature because the radiation pressure keeps on dominating after a certain time. So that was a theoretical idea, because it has some thermally unstable problem. But if we add a strong toroidal magnetic field above and below the thin disk, it shows that it could maintain the thin nature of the disk, which Oda et al. They have suggested long back in their several series of work. But the question was, who will actually supply continuously the generation of toroidal magnetic field? So for that, the poloidal magnetic field is pretty much necessary because it could develop the toroidal magnetic field with the help of dynamo processes. So that was the initial idea. And in their earlier work by Mishra, Mitch Begelman, and their group, they reported that if we consider this sort of configuration around the thin disk, they get some sort of elevated accretion flow. So our idea with Bhupendra was that whether around the FM torus, if we consider such kind of configuration, whether some after a long evolution, whether similar kind of surface accretion will be there or not. And we realized that initially MRI is developed within the torus and the magnetic pinching is happening. But beyond a certain time, we realize, I mean, obviously it is only up to 7500 gm by c cube, but we have checked up to 25,000 gm by c cube that the surface accretion is keeps on happening, and this is a plasma beta inverse, which shows that the surface region where Z by R is around 0.2 to 0.3, that magnetic field is much more stronger around that regime, and that actually drives the surface accretion, and it maintains the longevity of the system up to, even though we do it low resolution 2D, but our disk could survive up to a stable quasi steady configuration up to 25,000 gm by c cube. So this is the vertical profiles which you can see. This is a time average profile between 15,000 to 20,000 gm by c cube, and model A is the strongly magnetized case and model C is the weakly magnetized case, and this says that the density is much more lower than the weakly case because the surface accretion is much more dominant in the strongly magnetized case, and which drives the accretion matter much more faster. And this actually shows that the mass flux, that rho ur, which shows that around the surface region, if you see, that accretion is mostly happening around that regime. Now the interesting part is in panel E, if you can see here, that initially we started with only B theta, right? Like the vertical profile. But after a certain time, you would see that the toroidal magnetic field within the torus is the most dominant one. So that is basically, you could understand, if you start with a poloidal field, because of the dynamo effect, the toroidal field is keeps on developing, and due to the such generation, such sort of effect is keeps on happening within the disk, and eventually toroidal pressure is continuously developed. So that was the small runs that we did, and that this is the whole summary for us for today's talk. And yeah, and there are some open question also I would like to explore in future in my postdoc time, that is the global dynamics of Sagittarius A star. Because why I'm interested in Sagittarius A star, because Sagittarius A star is not so far confirmed to have a binary companion or having a Roche-Loeb overflow. Mostly the disk or some sort of matter is infalling from the Wolf-Rayet stars, which are basically wind-fed. So if we have a wind-fed accretion model, typically it shows a low angular momentum feature. Now, if we have a low to intermediate angular momentum feature, it could explain analytically several physics of Sagittarius A star. Now, recently there was this question that is being discussed in astrophysics community, that is the flaring events that has been observed in Chandra, and this famous variability or flaring events, this accretion community tries to explain with the MAT simulation, but they always over predicts this result. So recently there was some work where it shows that low to intermediate mass angular momentum accretion flow could actually explain those kind of, and even including a two temperature profile. This could be very interesting to explain such sort of global dynamics around Sagittarius A star, where our analytic solution could provide a deep insight, that I believe. So I am still interested in exploring such sort of low to intermediate angular momentum MAT simulations with a two temperature site in it. And finally, this I already mentioned about the spectral properties. And this is a paper by Begelman and Armitage long back in 2014, I believe. There they have postulated that magnetic flux could control the different spectral states, but there was no such evidence since I think last year they were doing some work with a postdoc there. Some sort of evolution they have explained with different kind of magnetic field topologies. And since in our shock work we have seen that the shock properties are getting controlled by the magnetic flux, we also believe in this thing that MHD turbulence could be very interesting to explain the variability or spectral properties of the X-ray binary sources. So this is all, I think. So thank you.
Thank you very much for the very interesting and complete talk. So now we have time for questions. Are there any? Yes, Carlos, please.
So, hello, thank you very much, Samik, for your talk, which was very interesting and covering a lot of aspects of accretion flows around black holes. And my kind of view was that you focused on potentially astrophysically relevant properties and the standard black holes. As you probably know, well, in our group, we are quite interested about alternative models of black holes and exotic compact objects. So, and I know that you worked on some astrophysical properties. I don't know if it's exactly the same type of accretion flows, but for some alternative models during your PhD. So my question is a bit generic, but I would like to know if your opinion, if you think these sort of models that you've been using, in particular these analytic models, they have any potential to, try to probe the space-time geometry and tell us something about potential Kerr deviations. Anyway, it's a generic question, and I would like to know your thoughts about it. Thank you very much.
Yeah. So, I mean, I would like to show you something. I mean, I forgot to put it in this work. I mean, in this today's slide. So, I was recently exploring something like obviously it was a Kerr-like black hole, but I was recently working on something with this naked singular spacetime. And for the naked singular spacetime, the solution is a bit different, which is obviously not a black hole, but a different. Obviously, you guys are more familiar with this kind of thing. So there are different things. Specifically, I was looking into the naked singular case with a higher spin, like around I consider 1.60 or something. And I realized if we have the radiative properties studied very well, like I did here for a black hole case, for the Carr-Topner black hole, which is the black one, and the naked singular one is the dashed case. This shows that the radiative properties could actually distinguish between these two profiles quite well, although it is not very significant to remove the degeneracy. But this is, I am really interested to look forward to, because there is a recent work by Kluzniak's group with this black hole accretion flow and this naked singular case, or maybe some sort of horizonless compact object. They actually show some sort of deviation could be there. And there is another work recently where, I mean, I was exploring everything analytically for the radiative properties, but here this group, they have shown if we have this horizonless compact object, some sort of photon arc could be developed around a naked singular spacetime. So this is a new aspect. I believe that could be very interesting. And regarding to direct to your point about the alternating spacetimes, I think that could be also interesting. But analytical point of view, if we talk about, the solutions might not be very different. Maybe we could see some different accretion solution topology. But from analytical point of view, probably we could not explore or explain much. But I believe if we go with these radiative transfer images, like there are several codes, I think that could probably resolve several open problems in the future. And maybe the polarization part also could play a very interesting role in the future to address this, I mean, to resolve this degeneracy. That I believe.
Okay, I think that was enough. So there's a line of work there to be pursued. I guess that's the conclusion, and some opportunities. Maybe we'll have the chance to discuss that well in the school or somewhere else. So thank you very much.
Yeah, you're welcome.
Then we also have a question by Hector.
Hi, Samik.
Yes.
Well, first of all, let me congratulate you because it seems that you did really a lot of work during the PhD.
Thank
So,
you.
well, I have several questions. The first one that I would like to ask is, in a real scenario, how likely do you think that these kind of structures would form? This is mainly because these flows that we are considering are isentropic, so they
Yes.
over a very large scale, no, from
Yes.
just up to thousands of RG, if I understand well. But in real life, so we know that is well, in general, every flow that is magnetized is unstable due to the magnetorotational instability. Of course, if the scale height allows, no, because it can also be that the magnetic field is too high and then it is suppressed. But so this means that this very ordered magnetic field would be eventually destroyed by turbulence. And also, if you have this assumption that the flow has no poloidal component, so if you include dissipation and if you have dynamo effect, it can be that the toroidal components become also vertical components. So they are converged.
Yes.
So what is your opinion on this? So is this realistic?
I mean, you are discussing about the shock model, right?
Yes.
Yeah, so I believe that if we have a strongly poloidal magnetic field, probably, we need to check. But recently there I was looking into these 2, 3 works by Indu, where they have started with this truncated accretion model. And they actually explained that some sort of continuous development of some jump kind of nature is developed. And secondly, I think one of I think your paper, which have this large scale feeding, there are also some sort of spiral structures, and which shows that some sort of shock kind of, although we cannot call it, I don't think whether we can call it a shock, but some sort of jumping nature is there.
Well, it is a shock. No, it is just not a standing shock because there
Yeah,
is no
so I
dissipation.
believe that in reality, standing shock probably, like in hydrodynamic case, people have observed and they have confirmed it with simulation. But in MHD, I don't think it is the case. Although analytically we could explain, that is the best we could do up to it. But simulation probably won't be able to explain the standing shock. But oscillating shock probably we could have. I mean, but not like this, like a such discontinuity. It will develop and keeps on moving. Those kind of
Right.
scenarios, I think probably it will be there, because mostly it will be controlled by the magnetic flux.
I see. So, well, may I ask another question? I have other two questions that I would like to ask, but I don't want to steal all the time.
Well, maybe Ivo has a question, and then maybe we come back to you, Hector. Is
Okay,
that
thank
okay?
you.
Okay.
Hello, can you hear me?
Yeah, I can.
Thank you for the talk. I think you've mentioned at some point about some features in the radial profile of these disks that you
Right.
expect to have an imprint on the image once you
Right.
do the ray tracing. Could you talk a little bit about this? I got a
Yes.
little bit lost on the details.
Yeah. So my idea is that there are several open source code that is available where the GRMHD simulation pipeline is already directed to that code, like IPOL or maybe some other codes are also there. Now, my idea is if I could include, and I am working on it, that I am trying to include directly from these accretion solutions into the IPOL, let's say up to 50 gravitational radii, and where we already know that this is the power law profile for it, which is typically fitting the flow. Now, obviously, your question is valid because we only have a radial profile in our hand. So, but in order to generate the image, which is probably a 3D profile, so for that you need the vertical profiles as well. So that is something we could give some simple Gaussian profile or some more realistic profile which all the other simulations or all the other papers, they have suggested some sort of density profile or temperature. There are a lot of different profiles. So my idea is radially we will supply this profile and assume some sort of vertical density approach, or maybe some series of vertical profiles we will try to fit with that code, let's say some X code that we will be using, and there using this 2D kind of effective 2D image that we will provide, that power loss, that could effectively generate some sort of intensity profile, and from there the standard technique to develop the ray traced images. I mean, not ray traced, but just the image that could be generated over there from the intensity profile. And then we could tally those images from the observed EHT images for the curved black hole, let's say. Then we could actually understand or constrain whether our radial profiles are good enough or not. And secondly, we could also say about the disk properties. Let's say if we have a very strong disk profile, I mean magnetic field within the disk, whether that could alternate this or alter this power law profile or not, that we also need to explore. So we could do a lot of things by simply introducing these power law profiles to the ray traced image, so that from the analytic solution also we could have the image, also polarization also I think we could calculate, because we already have this BR, B phi, and maybe if we consider some B theta in our calculation, we could actually develop some sort of polarization image as well in the equatorial plane. So that is the plan.
Okay, thank you.
Yeah.
So Hector, you can ask more if you want. For now, there's no other hand raised, so go ahead.
Thank you. So, well, the other question that I had is regarding the explanation that you proposed for the different spectral states of X-ray binaries. So, if I understand well, this this is explained based in your model that is also isentropic low angular momentum accretion that is magnetized.
Yes.
And you explained the difference between well the different spectral states by the location of the transition, no, between the two branches of the solution, the low entropy and high entropy one.
Like this region.
Well,
yes.
But in the traditional picture of the spectral states, so the two parts are very different in nature. So in your model, there is no there is no cooling at all. The flow is isentropic. But in the traditional model, the exterior part that produces the cold accretion disk profile, spectral profile, cools much more efficiently, right?
Right.
So how do you reproduce that part of the spectrum, the cold accretion disk part? Is it
like
possible?
Like the thin disk. So right now the model that we have, we probably won't be able to explain the thin disk part, like the black body portion from our model, because we only consider the subcaplarian branch and I mean the low angular momentum part all throughout. But for the standard picture, it was like outside it is a Keplerian model with high angular momentum, and the inner part is something like this, the puffed up model. So the idea is the initial model that was being proposed by Chakraborty's group, like they call it as TCAF model. There, what they did, they started that they assumed that the Keplerian flow is already there, but there is a subkeplerian halo that was present. Okay, so if you see the cyan branch here, this is the Keplerian flow, which is much more cold, and there you have a subkeplerian flow that is present here, and based on this subkeplerian flow, there is this puffed up inner part is happening. That was their initial idea, and that TCAP model says that there this shock location or the transition radius, then the temperature jump within the disk, and also the density jump within the disk, that could control the spectral properties. So since they haven't commented anything on the magnetic field so far, I just wanted to explain in this way that these properties could be also controlled by the magnetic flux. So that makes a one-to-one correspondence between magnetic flux and spectral properties. And eventually, when I read about this particular paper by Begelman and Armitage, where they were actually proposing some postulates with different magnetic flux accumulation, could explain the spectral parts at different region. So I believe that if some sort of similar simulations could be done, able to do this kind of framework, that could be very interesting to explain some sort of behavior of XRBs. That was the idea. But it's not very simple. It is not very simple. That I agree, because it's not very straightforward, because the shock in general if you go apart from analytic domain, it is not valid at all, I think. So that is pretty
Right.
true.
So you only aim to explain how how the magnetic field regulates the innermost
Yes.
part, no, the part that is already
Exactly.
radiatively inefficient.
Yes, that's true. So that is the point I need to think more detail about it, and I'm also trying to understand because there are a lot of works in this direction. They're thinking about it. I think this Jason Dexter, their group also working on some recent papers towards this. So I'm also reading those things. Let's see.
I see.
Yep.
Okay, well, one question more. So
Yes.
I am curious. So for the Pluto simulations that you showed, and also for making the ray tracing of to get the spectra
Yeah.
that you showed,
Hmm.
well, you need to put something in the rest of the domain because your solutions are only valid on the equatorial plane, right?
Yes.
So what do you do?
So above and below the equatorial plane, I am thinking initially to start with some sort of Gaussian profiles of the density, like simple z square by r, I mean e to the power minus z square by r square kind of profile in density, pressure, and all this stuff. And for the magnetic field, I am thinking to provide some sort of self-similar power law profiles, which are already existed.
I
So
see.
initially, my idea is to go with some sort of one or two different profiles, self-similar, Gaussian, or maybe some exponential profiles. So that was the initial idea that I have, and I was trying to incorporate it in the IPOL because in IPOL there is some modules where I could work on the quasi-spherical accretion model. So I was trying to look into it.
I see. I
Yeah.
see. Okay, thank you very much. Well, one thing before I was forgetting about
Okay.
it. So in the triangle plot that you showed with the Bayesian analysis, you spoke about some charge, right?
Yes.
I
Yeah.
missed that part. So which charge are you talking about?
Okay. So, I mean, this is basically, I think, this paper, charged particle of black bounce Reissner-Nordstrom geometry. So we consider a charged black hole uh, with a charged particle around it, which is revolving, and the central spacetime is black bounce Reissner-Nordstrom.
Okay,
Okay.
I see. So it's single particle dynamics, and you get
Yeah. Exactly. Single particle. So this m is basically the mass of the GRS source. Q is basically the charge of the black hole, and this small q is the particle's charge. And
I
this
see.
alpha
And the QPO
this
you get
R
it
by M is
from.
where
Okay.
the oscillation is happening. Yeah.
Okay. I see.
Yes.
Okay, thank you very much.
Yeah.
Those were all my questions.
Okay. Thank you.
Thank you. So are there any more questions? I will ask a quick one to let people think, but so actually it's a little bit on that topic as well. I was wondering if it seemed like with the shock, you had some different location of the shock depending on the angular momentum, or rather if your black hole was spinning
Yes.
more, there was
Right.
a bigger
Exactly.
impact. So could you also infer maybe the spin of the black hole from this kind of analysis, or?
In reality, it is not actually an analytic solution. When you have a lot of free parameters in your hand, right? So if you have a lot of free parameters, it is not easy to explain in that way. But I believe that I mean, in future, if these sort of equations could be pipelined with the simulations in detail, probably polarization study or the spectral fitting that I was showing in some of the plots, spectral properties could be able to explain some sort of feature. That I believe. But spectral feature only within the analytic domain, it shows that not only some what I can say, like there is some scaling up down will be happening, but the overall feature will remain more or less same. But from analytic solution, probably you won't be able to explain or separate or distinguish them pretty clearly. So it will
Okay.
only show that the sonic points will be different in a different location. That is the maximum you could expect. That's it. Nothing much. But the
Okay.
overall idea is that from the analytic solution, whether changing this magnetic field, spin of the black hole, whether this transition radius, which is still remains as an open problem in accretion domain from the hot flow to cold flow or the other way around, which parameters are actually controlling these features. So the analytic solution could give you an idea because for the simulation or from the theoretical point of view, how the thin disk suddenly forms a puffed up advective flow and where it is transitioning, that is not very clear so far. So from the analytic way, we could maximum say what are the factors that could affect this transition radius. That's it. So yeah.
Okay, thank you.
Yeah.
So, well, I see no other hands raised. So let's stop it here. Thanks a lot once again for this very good presentation and for the answers to the questions.
Thank you. Thank you so much. So